Morning, everybody.
Good morning, sir.
I think you don't need your tag anymore. I know who you are. Thank you for bringing your tag. How do you turn the sound off? I like the color. Shut up. I know you can turn it off. I have to keep the button pressed to turn it. No? Turn up. All right. So, morning all. And yeah, we have spectacular attendance today for 8, 9, 10, 11, 12, 16, 17 including my TA, 18 including me, right? So we're going to be talking today about generative adversarial networks. Before I continue, a shout out to two of my past TAs. Ben Streiner, who was my TA way back when, and he's the person who set up much of the class, and Howard Chen, who made some of these slides. So in the past couple of weeks, we spoke about variational autoencoders and diffusion models. What were variational autoencoders? What were VAEs? It had an encoder and a decoder, but what was the job it performed? What was it?
It's probabilistic.
It's probabilistic.
Transforms inputs into a latent space before.
Transforms inputs to a latent space, but was that the key purpose of the VAE? No. Then what was the key purpose? How did we introduce the problem? Anybody? Ara? We needed to learn the distribution. We wanted a sample from a distribution, right? And so we're going to be talking this week about GANs, which is another way of doing it. So here's what we learned in the last class, when you train a model for a task, there are a couple of different things you can do. You can have discriminative models. Discriminative models are, good. So have the purpose of trying to discriminate between classes. So you're given an input, you have to choose between a bunch of classes. So what they learn is the conditional probability of the class given the input. That's what we learned over the course of the semester, right? And so they really learn the decision boundary between classes. And so they can be used for classification tasks, primarily. And there are neural networks are not the only discriminative models. Logistic regression, support vector machines, all of them do the same job, where given an input, it tells you whether it's a cat or a dog, whether it's, the sound of a gun or the sound of of clapping, right? They're performing classification tasks. Given X, input X, they give you the probability of the class Y. Generative models, on the other hand, they are used to model distributions. They're trying to learn the joint distribution of the class label and the data. So they learn actual probability distributions. Now, given Pxy, you can perform classification, because classification is P of y given X. And using Bayes' rule, if I'm given the joint probability of X and Y, you can just divide by the probability of X, you get P of y given X, right? So the latter thing is more generalizable. But so in the second case, now if I model the distribution, I can generate samples from it, which means if I learn it from a bunch of data, I can generate more of the same. So they can perform both generation tasks and discriminative tasks. They vary a bunch of different models: naive Bayes, Gaussian mixture models. These are all classical models. These days we do it with neural networks. Now the problem with generative models is that there's a lot more to learn. The discriminative models are easy. If you have typically the number of classes you have is finite. Maybe it can be a large number, it can be 1,000, it can be 1,000,000, but it's discrete. And so you can learn to compute the probability of X, Y given X. Generative models, the input space is basically infinite in size, right? And so learning this model is a much harder task. So within this, we also come up with another distinction, things called explicit models and implicit models when we are speaking of generative models. In explicit models, I'm actually going to model the distribution for the data. Can anybody give me an example of an explicit model? You've learned this through school, high school, probably. What's an explicit model? An example? Come on, guys. Mohammed, I want an example. Of course you have an example. Somebody. Anyone on Zoom? Can you take a guess? How about a Gaussian? Yeah. Is a Gaussian an actual model for the entire probability distribution, right? Given an X, I can compute P of X because I have a formula for it. A Laplacian, a Gaussian mixture. These are all explicit models where you're actually learning a functional form for the probability distribution. So given an X, you can compute P of X. An implicit model is one where you actually don't know what to have a functional form for it, but you have some magical mechanism for drawing samples from this distribution. So an example of that, of an implicit model? A diffusion model, a variational autoencoder. All of these are implicit models, right? You can draw samples from the distribution, but you don't actually have. If I give you an X, you can't compute the probability for it. See the difference? So here's our first point. Okay, Muhammad is done. Somebody on Zoom, can you tell me the answer to the first question? Zoom? Is there anybody on Zoom?
It's the first one.
First choice, okay. Someone in class, can you give me the answer to the second question? The second choice, right? So generative models model decision boundary between classes? No. Discriminative models model the decision boundary between classes, whereas generative models model distributions, correct? And explicit models compute the probability of samples, whereas implicit models only let you draw samples from the distribution. You see the distinction and these two categorizations, right? So let's continue. We're going to be talking about implicit models. VAEs were implicit models. What was the problem with VAEs? What was the problem with VAEs, guys? The?
Stepping from the distribution to the image, like making one base.
So going from the Gaussian distribution all the way to the distribution of the data that you are trying, whose distribution you're trying to learn, was often one step too far. So it didn't do a perfect job. Your generations were not perfect. They got a kind of got the idea, but they didn't do a perfect job. And diffusion models, how did diffusion models solve this? By?
Performing small steps.
You did this by doing this in small steps. But then you could also have done this using nested VAEs, right? Where each VAE took a small step. What was the difference between a nested VAE and a diffusion model? Anybody? What was the difference? So when you train a VAE, you train both the encoder and the decoder, right? In a diffusion model, did you train the encoder? What was the encoder in a diffusion model? Can you speak up, please, Sunday?
Could be units.
No, that's the unit was not the. So what was the what was the encoder of a diffusion model?
The addition of noise.
You were just iteratively adding noise. This was in your control. There was no magical network that you were learning. All you were doing is adding noise so that all the way eventually it ended up as at a Gaussian. So an VAE, you're training both the encoder and the decoder. Does a crappy job because there's too much to learn. You could have staged it by nesting the VAEs. You'd probably do a better job, but then there's a lot more to learn. So the diffusion model went halfway, where you said, I'm going to learn only the decoder side. The encoder side is going to be handcrafted. I'm going to do this by adding little bits of noise. That make sense to you guys, right? So if somebody asks you the distinction, it's very clear. But in every case, here's the problem we were solving. You were given a large collection of data, say images, and you wanted to train a network to learn to generate new instances of these images, like lots of pictures of people. You want to learn a network that learns from these examples and learns to generate new portraits. Now, here's what the VAE did. The VAE is an example of something called reparametrization. What exactly do we mean by this? It's a mechanism. You see a very simple example of reparametrization inside a VAE. Every time you read about it, they tell you how they transform one Gaussian to the other. But the VAE itself performs reparametrization. What is it reparametrizing?
The distribution of the data.
The Gaussian is being transformed to something else, right? You're starting with a Gaussian. You're taking one distribution that you can handle, that's tractable. Then you're putting it through some crazy function here. It's a function that you learn, and then it gives you a new distribution, right? So that's a reparametrization of sorts, and then you're learning to sample from it. And this is what the VAE did. You sampled from P of Z, which could have been anything, but we chose a Gaussian. Why did we choose a Gaussian? Anybody? Why did we choose a Gaussian? Anyone? Because it's symmetric. That's half the part of the answer. Anybody else? Someone on Zoom, can you answer me? Why did we choose the Gaussian?
It adds random noise.
Yeah, but why Gaussian? Why not a Laplacian? Why not something else? So someone asked this in class, Zoom. And the answer is very simple. When you, if I fix the variance of all the distributions in the world, which one is the least informed? Which distribution has the least structure? Can somebody answer me? Can you speak up, please? Gaussian. It's a Gaussian, right? The Gaussian has the highest entropy of all distributions for a given variance, which is why in the central limit theorem, as you keep adding noise, it doesn't matter what kind of noise you add, what do you end up with? Gaussian. So what does that tell you about a Gaussian? It's probably the most noisy distribution. It is the most noisy distribution you can think of. It has no structure, right? And so the reason we choose a Gaussian, that makes sense to you guys, right? You're familiar with this concept, right? If you've heard about the central limit theorem, you know it always keeps, every time you add independent variables, it goes towards a Gaussian. You're making this less and less informed. And so we choose a Gaussian because the Gaussian makes no assumptions about the data. Anytime you want to, you choose something other than a Gaussian, you're making some assumptions about the distribution. You're imposing some structure you don't want to, that's all. I mean, if you know something about the nature of the problem, you could have different P of Z's. People have tried working with HMMs and stuff like that also. But the point is, this is the most uninformed. And so this is the VAE, right? The generator over here is the decoder of a VAE. You sample from a Z, you pass it through the generator, it generates examples from your class. And so the way we learned it, it's actually a parametric model. The parameters are the parameters of the function G, right? This is the generator. It's generating samples from the distribution. But when we learned it, we realized that we're doing this through a reconstruction process. Your X goes in, you get a Z, Z goes in, X comes out. The reconstruction is never perfect. Why is the reconstruction never perfect? Anybody? We were speaking of manifolds and such like, yeah.
The reconstruction can only occur on that plane or on the surface that the VAE is.
The reconstruction can only happen on the manifold that's captured by the VAE. Variations of this manifold must be accounted for by noise, right? And so here's the structure that we actually had. Samples from Z go into the generator, and whatever comes out is going to be on the manifold. To account for the stuff that's off the manifold, you have to assume that there's a noise. And so the way we trained the network was to minimize the noise, which was the same as saying, in the ideal case, the noise must be Gaussian. Why did we say that in the ideal case, the noise must be Gaussian? If everything is well learned. Anybody? Why would the noise have to be Gaussian if everything is well learned? Anyone?
That means you've learned all the information.
You've learned all of the information in the data because the Gaussian is the most unstructured noise you can get, right? If there were structure left in the data, your learning should ideally have captured it, correct? That makes sense to everybody, right? And so this is basically what we did. We said there's an error, and this error has to be minimized. We're going to assume that it's Gaussian. We're going to learn the parameters of the generator to minimize this error, which is to say you're going to maximize the log likelihood of your training data, or alternately, you're going to be minimizing the negative log likelihood of your training data, which is your standard training paradigm for any neural network. Everybody good with this? This is how we learned VAEs. Now, VAEs are trying to learn to generate, say, faces. But the way you're training it is by maximizing a log likelihood. So is there anything about log likelihoods that informs about faces? Is this directly connected to faces? Say if I'm trying to generate faces, right? So you're sort of hoping that this mathematical abstraction of maximizing the likelihood somehow trains the network to learn to generate faces, right? And so likelihood maximization does not actually relate to whether the output actually looks like a face. Does it? Likelihood, it's some abstraction. You have no clue what it means. Somebody told, some mathematician, some statistician, some guy sitting and writing papers, and neural networks told you, hey, do this. And so you just believe it. We're all cattle. And we maximize the likelihood. Magically, it seems to work. But then, if I come back to you and say, suppose You're starting from scratch, right? Think of yourself as a person. So if you think of yourself as a person, and if I'm trying to draw faces and you're trying to teach me to draw faces, then how would you go about teaching me? What kind of feedback would you give me? I draw a circle, So I'm correcting myself, right? And I'm going to learn this in a stepwise manner. So I'm trying to learn faces. I look at Rutvik and I draw this. Okay. What would you tell me? How would you give me feedback? Yeah.
Each feature you would
For each feature, but the simplest thing you're going to say is doesn't look like Rutvik, right? That's about it. That's really all you're going to tell me. I mean, you can give me finer corrections saying that ear is wrong, the hair is wrong, the nose is wrong. At the highest level, is this Rutvik or is this not, right? Or if I'm trying to draw faces, and I start off by drawing something of this kind. This is my picture, and I drew this, and I said this is a face. What would you tell me? Can you say that aloud? It's not a face, right? This is the level of feedback you really want if you're thinking of it in a semantic sense. Yes or no?
Yes.
Right? This is what you really want to do. Right? Can we make the training criterion more direct? I want to draw faces. I have drawn that absurd blob. You are going to tell me that's not a face, right? So if I want to put that in math, I want to say, does it look like a face? Right? Yes or no? Okay? And how would you mathematicalize it? How would you operationalize something of this kind? Does this look like a face? Can you speak up, Sunday?
Measure the distance between the actual face and the face.
Is that what you're going to do? Is that what you just did when I plotted this and said this, I drew this and I call this a face? Did you measure distances or what else did you do?
Yes or no answer.
You just gave me a yes or no answer. That's not a face, right? How would you make one up of that kind there? Yeah? I can just train a class, put a classifier over there. Its only job is to say whether it's a face or not. Okay, can somebody answer that first question, true or false? Is everybody sure it's true? Okay. What about the second one? Someone on Zoom, can you tell me? Which are the statements that are true? Zoom? Can you give me the answer to the second question?
I said the first one.
The first one. Okay. All right. And for the third question, someone here want to give me an answer?
True.
True. Okay. So VAEs are implicit generative models. Now, likelihood maximization may not result in a model that produces more face-like outputs because the model can maximize the likelihood of the training data without any assurance about what other non-training samples can look like. So, on the training data, it can reconstruct the data just fine. Then off of it can generate random noise, cats, dogs, what have you. And furthermore, I'm sorry. Okay, let me turn my phone off. Okay. So The phase generating model is more likely to generate phase-like images if it were trained with a differentiable loss function that explicitly evaluates if the output looks like faces or not. This is also true, right? And so that's what we're going to do. We're going to have a module at the end which looks at the output of your generator and says, does this look like a face, just like you would? And so that leads us to generative adversarial networks, right? So what are GANs? The term generative adversarial network has 3 terms. The first term is generative, because these are generative models which generate data similar to the training data, like a variational autoencoder. But these are adversarial because they are trained using 2 competing networks that are trying to beat one another. The discriminator, which is giving you your Delaff loss. Does this look like a face loss? That's learning to discriminate between the output of the network and real faces. And then the generator, which is trying to cheat this guy, right? And of course, the whole thing is a neural network. So that's why it's a generative adversarial network. So these were introduced originally in 2014. The goal is to model P of X, the distribution of the training data, so that the model can generate samples from P of X. And you train this using a pair of models which act as adversaries. You have a generator that generates data and a discriminator that evaluates this, the output of this generator, the so-called, what I call the Delaff loss. And here's what it looks like. The generator is just like the generative end of the decoder of the VAE. We know the decoder of the VAE is a generator. I'm going to sample random noise, you put it through the decoder, I get data. Now that output goes into a classifier, my Delaff classifier, the one that you guys just told me you could do, which is going to look at it and say, does this really look like a face, right? And if no, then it's the generator has to go back and correct itself, right? And so how would the discriminator itself operate? It has to know to distinguish between real faces and the output of the generator. Okay, so given this, first let me ask you a question before which I don't expect you to know the answer. Can I just take a classifier which does a really good job of making out faces versus non-faces and use that? Can I? Go back and look at this question, right? If I just look at this and say this is not a face, is that good enough? Yes or no? No, yes. Can you speak up? How many of you think no? Okay, everybody thinks no. So why?
Because like just saying yes or no like does not allow you, does not contain information on how wrong.
It doesn't contain information at how wrong it is. So I say no, and so I go ahead and add little shrubs over here, right? You're going to keep saying no all the time. Just saying yes or no is not a good answer, right? So you don't want a perfect discriminator. Having something that's been perfectly trained and you throw it into the mix is like this guy. It's useless. I mean, it's not entirely useless, but it's effectively useless, right? You want something that's slightly better. And so here are the 2 components, the generator, which transforms samples from the random noise to things like faces, and the discriminator, which can tell you the difference, whether it's a good one or not. And the key is in making sure that the discriminator can inform you properly. It should say this, you know what, that doesn't look like a ear. Or, first, to make something that's just a single round thing. And then you have to correct it one step at a time, right? Make sense to everybody? Right? You guys agree with me on this, right? So what's the generator? The generator's job is to produce realistic looking X. It's operating on this latent sample Z, which comes from your noise distribution. And that goes in and generates G of Z. So, and Z is going to come from some prior. And the prior we chose was Gaussian. Again, why did we choose a Gaussian, Myra? Because it's noisy? Well, no. Why did we choose a Gaussian?
Uninformed.
It's maximally uninformed. It's the most noisy noise you can think of, right? And the goal is that when that Gaussian has been transformed by my generator, the output distribution must be the distribution of real faces so that when I sample from it, what I get are real faces, right? And the discriminator's job is to tell the difference between real and generated data. Specifically, so here's the thing. I don't care about a perfect discriminator. I don't want a classical artist coming and tell me, nah, this is not a face. You want something that is working with you. Like when you are a teacher, when you're working with students, you have to adapt your teaching style to the mistakes the student makes so that you can guide them through the process of learning. Just having a perfect discriminator is going to be a totally useless thing. And so you need a discriminator that can distinguish between the output of the generator and real data so that it can guide the generator in the correct direction. Make sense to everybody, right? So, and which means the generator and the discriminator must both be trained. A teacher who learns, who knows how to teach kindergarten kids is going to be completely useless at teaching people who are pretty good artists and vice versa, right? The discriminator is the teacher. It has to adapt itself to the generator. Make sense? Right. So how do you train so where would you start if I want to train this? Would you start out by training the generator? Or would you start out by training by the discriminator? The generator is noisy, right? Initially, it's going to be random. And so the discriminator is the guide. The first person to learn is always the teacher. You can't have the student learn before the teacher. So you'd have to start with the discriminator, right? And so the discriminator is going to, is provided training examples of real faces and data that are generated by the generator. And it's going to learn to distinguish between the two. So it's going to, now, these are not teachers, these are classifiers. It's a binary classifier. So it's going to operate on some input X and generate D of X, yes?
We just said we're going to give the discriminator real photos and then generate it.
Yes.
How are we getting the generated if we don't already have the generator?
When you start off training, how is the generator initialized?
Don't have the generator.
It's just randomly initialized. I can feed it Z's and it's going to generate some output, correct? Yeah, right. So, yeah.
As to this question, like, do you learn the two of them in parallel or you learn one first?
Hang on. Okay, so wait for it, right? So here's what this is doing. Here's the discriminator. The discriminator is operating on the input X. It's a binary classifier. The ideal output should be 1 for real faces and 0 for fake faces, right? So the discriminator has to be 1 for real faces, and 1 minus D of X must be 1 for synthetic faces. You guys agree with this one? Right, okay. And so if I want to train the discriminator, I want to push D of X towards 1 for real faces and 1 minus D of X towards 1 for synthetic faces. In other words, I want to maximize log of D of X for real faces, and I want to maximize log of 1 minus D of X for synthetic faces. Everybody good with this so far? Right. And once the the discriminator has learned to distinguish real faces from synthetic faces, then what must the generator try to do? It must try to fool the discriminator, right? So in other words, the generator must try to maximize the output of the discriminator on the stuff that it generates. So you want D of G of Z, D is the discriminator of G of Z to be going towards 1, or 1 minus D of G of Z to head towards 0, right? So everybody good with this? And so I want the generator to be trained such that 1 minus D of G of Z goes to 0. It's as small as possible, or alternately log of 1 minus the D of G of Z to be as small as possible. I want it to head towards negative infinity. So if you put those two together, here's what you have. The discriminator for real data, you want to maximize log of D of X. For synthetic data, you want to maximize log of 1 minus D of the input, right? And the generator, you want to maximize log of 1 minus D of X, right? So you can see that the two are at odds with one another. One is trying to minimize these two terms. One is trying to minimize this term. The second is trying to maximize these two terms. Everybody good with this? And so if I want to train the whole thing is going to be jointly trained like so. I'm going to have a loss. This guy, log of d of x, must be computed over a whole bunch of training data, instances of real faces. What are instances of real faces? Instances of real faces are samples of x drawn from P of x. P of x is the distribution of real faces, right? This guy, the second thing, must be maximized over instances of synthetic faces. What are instances of synthetic faces? Samples drawn from P of z and pushed through the generator, right? And so this first term is the expectation over x, the distribution of real faces of log of d of x. The second term is the expectation over z, samples drawn from z, of log of 1 minus d of g of z, right? And the discriminator is trying to minimize this guy, and the generator is going to try, it doesn't take, is not dealing with real data at all, but the generator is trying to maximize the second guy. This makes sense to everybody? Questions? Any questions? Right, so it's a min-max problem. One of the two models is trying to minimize this loss. The other model is trying to maximize this loss, okay? So this is what you do. You're going to start off with training the discriminator using the current generator. Then fix the discriminator. You want to train the generator. Fix the generator. You want to train the discriminator. Which of the two must be trained more? Generator? Who needs to be more skilled, the teacher or the student? The teacher. So who needs to be trained more? The discriminator has to be trained more, right? At each point, you update the discriminator for a few steps, and then use the discriminator to update the generator. Okay? So here's your problem. Okay, this was a simple one. Someone on Zoom, can you answer the first question? Someone on Zoom?
Discriminate.
Okay, and somebody here, can you answer the second one? Also, right? So when training again, you must first train the teacher, the discriminator. The discriminator is computing the, does this look like a face loss, the Dirac loss, right? And the discriminator again, you always have to teach the teacher first. And so the discriminator has to be updated more frequently, right? And so here's the whole thing. I have a generator which takes in samples from a Gaussian, tries to convert it to real faces. I have a discriminator which can try to distinguish between the output of the generator and real faces. So how does the whole thing behave? Let's look at what the optimal discriminator will do, okay? So again, here's the thing. Suppose I have a distribution of this kind, that is the distribution of synthetic faces that my model is currently generating, okay? And I have a distribution of this kind, which is the model distribution of real faces. Okay, so this is synthetic, this is real. Now I get a data point out here. Okay, what is the probability of this having been generated by the real, being a real face? That's this height, correct? That's probability of x and it being real. This height is the probability of x and it being synthetic, right? And so on this picture, first, what do you want the discriminator to do? You want the discriminator to distinguish real faces from synthetic faces, right? So what kind of rule would the discriminator apply over here on this picture? So if this is x, if the input is just one dimensional, what kind of rule would the discriminator apply? Anybody? Come on, guys, you're better than.
Boundary which tallies the difference.
Okay, what is that boundary? A dot. What is that boundary over here? Anybody? You're dying to tell me, so go ahead. Okay, let me answer this. On this side, over here, are real faces more likely or synthetic faces? On this side, where's the crossover?
Like
Intersection.
Right here, right? So what must the discriminator do?
Minimize.
Mhm.
Minimize.
The discriminator's, what is the discriminator's job over here? It's trying to, come on, guys, wake up. What is the discriminator trying to do? Is it going to have to have coffee? What is it trying to do? Then,
Minimize S minus R. It's going to
What's that?
try to minimize S minus R.
Try to minimize minus. But what is the discriminator's job in life out here? Its job in life is to look at X and tell you whether it's a real face or not. Yes or no? Yes. Can everybody say yes?
Yes.
Okay, some of you guys there, say yes. Okay, don't sleep on me. All right, so given this, the discriminator is going to output a 1 or a 0, right? Where would it output a 1?
On the right.
This, on this side. So here's the boundary, okay? And on this side, you want it to output a 1, right? And on this side, you want it to output a 0. Does that make sense?
Yes.
Right? And right at the boundary. But would that kind of a discriminator be informative?
No.
No, why not?
tell you more about the face making worse.
It doesn't tell you which way to shift, correct? So if I've got something on this side, if I have a synthetic data point, and the synthetic data point is out here, it's not telling me whether I should move right or move left to make it more like a real face, right? So what kind of a discriminator would be more useful? Something like a, go ahead, say that aloud.
Sigmoid.
A sigmoid, which tells me how far away you are from the boundary. Make sense, right? And so you want the discriminator to be something like this, with a 0.5 out here. So what is the ideal discriminator? The ideal discriminator is a Bayesian classifier. It has to tell you what is the probability that this guy is a real face. Then you can keep pushing it to increase it, right? And so that is simply going to be P of X comma R divided by P of X comma R, P of X comma S, right? So this is going to be your ideal discriminator, right? And so that's basically what your ideal discriminator is. It's the probability of the real face given the data. That's what you ideally want it to be. And now you can read this probability. You can look at it and check, compare it to 0.5. And based on whether it's greater than 0.5 or not, you can decide whether it's a real face or not. So this is both answering your question, is this a real face or not? But it's also telling you which way to move X, right? Okay. And so the perfect decision boundary is where P of y1 given X is P of y2 given X. The perfect discriminator will compute this for each class. This is the ideal discriminator. A discriminator which is just, anything that says this is a face and this is not, with an optimal decision boundary is still a discriminator. It's just not good enough to learn from. That's all. Okay? So now, how does the whole thing work, right? This guy here, where the two distributions cross over, that's the optimal boundary, correct? And so now let's say this. Work with me out here. So is everybody good with this so far?
Yes.
Okay. And so Now I want a chorus answer because it's 8 in the morning and everybody must wake up. And so let's say this is the distribution of real faces. This is real. Okay? And this is the distribution of the data that your synthetic faces that your current generator is generating. Okay? Then the discriminator, you've trained your discriminator. If you train your discriminator, what is it learning? It's learning this boundary, correct? It's saying everything to the right is a real face, everything to the left is a synthetic face. This is when it's going to make the fewest errors. Okay. Now, you have this discriminator and you are allowed to train your generator. What must the generator do? It's going to modify the x's. It's going to modify the distribution of x's. What must the generator do?
Shift S in direction one. Make the discriminator more likely to.
So how would it do that again? Shift, yes, shift what? You want to shift this distribution out. It has to say, okay, I want to fool this guy. Let me move this out here. And then when it does that, now it's beginning to fool the discriminator, right? But then the moment you, so that's basically what you want to do, right? You want to shift this after you train the generator. But then you've trained the generator, and now it's beginning to fool the discriminator. What should the discriminator do now? It can? The discriminator must learn the new boundary, right? So the discriminator is now going to say, okay, this didn't work. This is the new boundary. Then you go back and learn the generator. What will the generator do?
Move further.
Shift it further to the right, right? And so then the generator is going to shift this further over here. And then what will the discriminator do?
Learn the new boundary.
When will the process stop?
When you reach the
When the two are no longer distinguishable, right? So the discriminator learns the perfect boundary. The generator shifts the distribution right. Then the discriminator learns the new boundary. The generator shifts the distribution right? And they keep doing this back and forth until the two are sitting on top of one another. There's nothing the discriminator can tell you anymore. Make sense to everybody? Right? At this point, anything the generator generates is going to be indistinguishable from something that the discriminator can, from the distribution of the real data in the ideal case. Okay, so this is your GAN. And the optimal discriminator, of course, is going to be a Bayesian classifier, which is P of x divided by, which is the probability of real and x divided by probability of real plus probability of synthetic. This is just a Bayes rule, okay? Now, what exactly is happening mathematically? So is everybody good with this so far, right? And are you also okay with that? This is the ideal discriminator. This is the posterior probability of the real given the x. So let's go back and look at the math and say, what is the... I'm sorry. Come on. Won't even let me turn my phone off. Okay. So what happens when I have an ideal discriminator in each case? Let's assume that at each point, you've trained the discriminator so that it's doing a perfect job of computing the posterior probability of the real class. Okay? So that is to say d of x is simply the posterior probability, which means I can plug this d of that formula here, right? So with a perfect discriminator, this d of x is going to be this guy, right? And same thing over here. This is x is this generated data in the second case. If I plug that in, I'm going to write this formula over here into this loss function. This is taking the expectation over samples drawn from the real distribution of faces. This is the second term, except that the 1 minus d of x is going to replace px with pg, right? Over here. And this is an expectation taken over synthetic, the distribution of synthetic faces. Okay? This guy is the actual loss that the GAN is minimizing. What is it doing? This is minimizing this term, which quantifies the difference between the distribution of real faces and the distribution of synthetic faces. And how does it quantify it? Now, what is the most common way of quantifying the difference between two distributions is the Kullback-Leibler divergence, right? The Kullback-Leibler divergence is given by this guy, summation over x, log of p of x over q of x. So p is the real data, q is your model. Now, what is the problem with the first statement, with the first formula? P times log p over q. Where can it break down? When they're the same? Where can it break down, guys?
It tells you nothing about.
Where can that formula break down?
When Q becomes 0.
Can you speak up, please?
When Q becomes 0.
When Q becomes 0. So if your current model assigns 0 probability to a real face, then that formula is going to give you log of 1 over 0 minus infinity. It's no longer differentiable, the thing breaks down, right? But then I can define KL divergence in two ways. I can define it as P log P over Q or Q log Q over P, right? So if I define it the second way, then what's the problem? What is the issue here? If P becomes 0, if my model is assigning a non-zero probability to something that's impossible, then suddenly my KL divergence is no longer computable. I'm not going to be able to minimize this. Does this make sense to everybody? Right? And so the KL divergence, which is what we were doing when we were using our standard loss functions, was not great. But then here, what we are minimizing is the Jensen-Shannon divergence, right? And also this is not symmetric, right? There's something called the Jensen-Shannon divergence, where if I'm trying to find the difference between two distributions, I compute the average of the two distributions. So I'm going to compute the average of P and Q. And I compute the KL divergence between P and this average and Q and this average. And observe here that the only time the denominator becomes 0 is when both P and Q are 0. But if both P and Q are 0, you're going to end up with a 0 log 0, which is really 0. So this doesn't suffer from this blow-up problem that you just saw with the KL divergence, right? And so that is, this guy is summation P log of P over P plus Q, 0.5 plus 0.5 summation Q log of Q over P plus Q. Okay, and this is the Jensen-Shannon divergence. And let's look at what the GAN, right, is actually computing. What does this look like? It's actually, sorry, this is going to be, there's a 2, because P plus Q over 2, right? And so what does this guy look like over here? It looks just like the Jensen-Shannon divergence, right? To within a scaling factor. To be precise, it's 2 times. So this log of 2 over here comes out as a plus log of 2, a separate term, right? And so, and this 0.5. So if I want to convert it to this guy, this just ends up being 2 times the Jensen-Shannon divergence minus log of 4. Okay? So what this GAN is doing is basically minimizing the Jensen-Shannon divergence between the real distribution and the distribution of synthetic data, right? And this only works when the discriminator has been trained to be the optimal discriminator at each step. But that's the assumption that we're going to be making. This makes sense to everybody, right? And so the optimal generator minimizes the Jensen-Shannon divergence between the distributions of the actual and synthetic data. It tries to make the distributions maximally similar, okay? And so when that happens, the generator of the fully optimized GAN will generate P of G equals P of X, Px of X, okay? At this point, for any given synthetic distribution instance or real data, what is the probability it's going to compute for, what is the output of the discriminator?
0.5.
It's always going to be 0.5, right? Regardless of the X, the two distributions are identical, so it's always going to be 0.5. In other words, if I have my X and I have the output of the discriminator, at every X, the output of the discriminator is 0.5. That's what it's going to look like. So now, what is the derivative of this guy? 0. There's no more divergence going back. And so, there are no further updates, okay? That's a stationary point, right? So if all goes well, then when your generated data and the synthetic data have the same distribution, then the discriminator is a flat function, and no more divergences go back, and the model is perfectly learned. But then can you give me some other thing where the discriminator also gives me a flat function of this kind? An example. Just a random discriminator, it always outputs 0.5, right? Is that going to be useful? No, right? So a discriminator, a random discriminator, we just randomly assigns thing to one class or the other. That's also going to have an error of 0.5, which means that the initial discriminator has to be trained. We said that, right? If a random discriminator is going to also not let you learn, and there's something else that will not let you learn. What kind of discriminator doesn't let you learn? We mentioned this a little while ago.
One that is too sure.
One that is too perfect, right? That thing is not going to let you learn because there are no more derivatives, okay? So this turns out that GANs are really challenging because a discriminator that's random is not going to let you learn. There's nothing more to learn over there, correct? And so which means you can't even update the discriminator at that point. There's no derivative whatsoever, correct? Second, a discriminator that's too sure is also not going to let you learn. And guess what? You're going to keep falling into these two bins so frequently that training GANs is really, really annoying. And so you need to train the generator and the discriminator simultaneously. If the discriminator is undertrained, it provides suboptimal feedback. If the discriminator is overtrained, there is no local feedback, okay? And so here's the overall process. You're going to train the discriminator, then you train the generator, you keep going back and forth. When you're done, you don't really need the discriminator anymore. The generator is what is going to be used to generate data. And so GANs can produce really, if they're properly trained, they can produce clear, crisp results for many problems, but they have stability problems that are hard to train. There's such a thing as mode collapse, and we will get to that in a bit. But first, there's your final poem. Okay. So someone want to tell me if the first statement is true? Yes or no? Okay, everybody answer me. Is the first statement true?
Yes.
No? Okay, some said yes. What about you guys? Yes or no? Okay. What about the second statement?
Yes.
Yes.
Third?
Yes.
Fourth?
Yeah.
Right? All of them are true, right? A generator that always generates the same phase can fool the discriminator, right? If it learns to generate one phase, just one phase, poor Ruthwig's phase, it doesn't matter what you feed it. It's going to fool the discriminator. Your loss is 0, but is that a useful model? No, right? You want to have variety, right? That's mode collapse. Now, the Jensen-Shannon divergence can have poor derivatives regardless, and we'll see some examples of how, right? Which can prevent learning. The discriminator may be random, in which case also you're not going to learn, right? And the discriminator may be too certain, in which case also you're not going to learn. So before we proceed into that, just to summarize, the difference between VAEs and GANs, it minimizes the KL divergence between the distributions of synthetic and true data. We started off with VAEs, chopped off the decoder of the VAE, and then we put in a Dirac loss, right? And the GANs minimize the Jensen-Shannon divergence between the distributions of true and synthetic data. VAEs use an encoder to predict the latent distribution to optimize the generator. GANs use a Dirac loss. They use a discriminator, a teacher, to train the generator. And so VAEs have the more complex formulation. We went through the math. It was fairly tedious. But then it optimizes very easily. On the other hand, the results are blurry. GANs, the math is simple, but training it is really hard because it has all kinds of issues. But the results can be very good, right? Here are the outputs from the first GAN paper back in 2014. Not so great except for digits. But then, they just kept getting better. 2014, 15, 16, 17, by 2018, you had these really beautiful faces and landscapes and whatnot, right? Star GAN, this was 2018, where you learned how to manipulate data. Progressive growing of GANs, where you ended up, where people figured out how you can generate 1 million and 4 million pixel images using GANs. And here are some examples. I mean, brilliant, right? I'd like to eat that spaghetti. It's really good. The mushroom looks so lifelike, and this dog could be your pet. Amazing stuff, right? So these things are very powerful, but then you still have many issues, right? There's some shortcomings, and we'll look at those in the next few minutes. We're going to look at some shortcomings of GANs, how you can, some variants of GANs, simple examples. I'll probably skip that and just look at some GAN applications. So we're going to look at least squares GANs, the Wasserstein GAN, conditional GANs, progressive GAN and style GAN. I have the slides, but I won't talk about it. I'll just talk about image-to-image translation and text-to-image briefly, okay? So what is the problem with the vanilla GAN? The vanilla GAN is that the discriminator can get too good, right? And if the discriminator gets too good, then you won't learn anything. Also, if it always produces the same output, then your loss seems to think everything is fine, but it has not really learned everything, right? How can we deal with these? We're going to deal with this one step at a time. So here's the example of mode collapse, right? This was from Ian Goodfellow's 2016 tutorial, where you're trying to learn that distribution, which has 6. It's a mixture of 1, 2, 3, 4, 5, 6, 8 Gaussians. But if the model learns just one of the Gaussians, as far as your loss is concerned, it's perfect, right? And so this is mode collapse. So the problem is this. There's a twofold problem. Here is the ideal behavior, right? At the optimum, the discriminator has no more derivatives because the loss is just flat. At every x, the output is 0.5, right? But then, if I'm not at the optimum, if I'm perfect, then the discriminator becomes flat, right? And even if so here's the thing. In a situation like this, when I'm far enough away, even if I'm using a sigmoid, what is going to happen? Right? If my initial data are out here, real faces, synthetic faces, what is your sigmoid going to look like? Because they are so far apart, right? It's going to just say, oh my. Out here it's going to be flat, out there it's going to be flat. Are you really learning anything? No, right? So even when you're going off with the software losses, things can break down, right? And so here's a very nice little example. Let's say I have real data. The output is always 0, okay? And my synthetic data always produces an output of theta. What do you want to do? I want my synthetic generator to push the theta towards 0, right? But what does the KL divergence look like? The real data is a point mass at 0. The generated data is a point mass at theta. And so for real data, I have something that looks like this. For real data, I have, this is P real, this is 1, and this is 0, right? Out here. For synthetic data, this is 1, this is 0, and this is 1. Because they are far apart, okay? So if you look at the KL divergence, if I look at it as, please, this is going to be 1 times log of 1 over 0 plus 0 times log of 0 over 1. This is 0 over here, so the second term won't matter. But look at the first term. There's a log of 1 over 0, right? The KL divergence is going to break down. Does this make sense? Right? Now, so the KL divergence doesn't work. We thought we'd fix this using the Jensen-Shannon divergence, right? Does that really happen? If I use, that's a useless board. Okay. So now, if you look at the Jensen-Shannon divergence, the generated data is again theta. The real data is 0. If you look at what happens if you plot the Jensen-Shannon divergence, there are 2 terms, one at 0 and one at 1, right? So for theta not equal to 0, you're going to get 1 log 1 over 0.5 for the Jensen-Shannon divergence plus 1 log 1 over 0.5 because both of them are the same, right? That's simply going to be log 4. If theta is 0, so anytime the synthetic and real data are not identical, the Jensen, regardless of the value of the synthetic data, the Jensen-Shannon divergence is just log of 4. Because where one is 0, the other is not. Where the other is 0, the first is not. So together, the 0 they just 0 out, right? Where p of x is 0, the term becomes 0. Where this probability of the synthetic is 0, the term becomes 0. Overall, it becomes a constant. The Jensen-Shannon divergence doesn't tell you which way theta must go, right? And if theta and if the real and synthetic data are exactly the same, then the Jensen-Shannon divergence is 0. And so what you have is, if I have theta, in this example, if I have, say this is theta, right? And I'm plotting the JS of synthetic versus real. When theta is not 0, this is log of 4. Correct? When theta is 0, it becomes 0. And then it goes back to log of 4. Is this making sense to you guys? Right? So this is not differentiable. So how can we fix this? Neither the KL nor the JS divergence are any use. So one thing we want to do is to say that in this case, let me see if I can pull this and whether it will stay down. Our situation was, this is my real data. This is my synthetic data, right? And both KL and synthetic and JS were not sensitive to how far theta was from 0. They gave you the same answer regardless of whether theta was here or theta was here. So how do you fix this?
Measure the distance.
You want a loss that is actually sensitive to the distance, right? So one of the first things we do is least squares GAN. Okay, there are 2 different things. One of the reasons here, one of the problems here is that it goes to infinity because of a 0 in the denominator with KL, right? So if I try to fix the KL, I can try to fix this by saying I'm replacing the KL by the L2 divergence, which we considered way back when. That gives us our so-called least squares GAN. The least squares GAN gets over the fact that, you can get log of minus infinity in your loss. And so it solves one problem. It doesn't solve the other problem, namely that, if the discriminator is misbehaved, then the least square scan doesn't really tell you anything useful. So that was one of the first. This least square scan is actually one of the more popular losses for GANs, where instead of the KL divergence that we were looking at, people look at the squared Euclidean distance between d of z and 1, okay? But the more important, interesting one is the so-called Wasserstein distance. Now, the Wasserstein distance is a very ugly thing. Nobody knows what it is. So it's amazing. Now, it's called the Earth mover distance. And the Earth mover distance is, if I have a pile of, say, Earth out here. So this is my pile of Earth. And I want to convert it to a different pile which has this shape out here. Right? I can move each, this is my probability mass, but if I think of this as piles of Earth, I can move a little bit of this guy to here, right? I can keep moving little bits of the volume over here. And so where do I pick this? If I pick something from here and move it here, then I'm spending a lot of effort, because I could have moved them out here instead, and I'd be spending less effort, right? So if you think of transporting masses from one point to the other, then there's an optimal transport where you say, how much of this mass do I take and where do I take it to the other pile? And if you do this optimal transport, then that's going to give you, the less work it is for when you're performing the optimal transport, the less different the two piles are, right? If the two piles are identical, you don't have to transport anything at all. So the Earth mover distance was actually invented in a different context, literally about the optimal transport problem, but it turns out we can also use it to compare probability distributions, because at the end of the day, a probability distribution is just a pile, right? And so how do you, where you're considering how much to move each bit. And so the total mass times distance required to transform one distribution is what you want, and it's symmetric, right? The effort taken to move this guy there is the same as the effort taken to move that guy here. The problem is that coming up with the optimal transport plan is impossible. It's NP hard in some sense. It's because you have to if I think of it this way, right? Here I can think of this mass as many little pieces all stacked together, correct? I can think of this mass also as many little pieces all stacked together. And the question you're asking me is, where does each one of these balls go on this stack, right? So if I have like 1,000,000 balls over here to fill this stack, and I have 1,000,000 balls over here, there's 1,000,000 raised to 1,000,000 possibilities. You're really not, and you have to explore all of them to decide what is the optimal transport. And so the optimal transport problem is an open problem. There is no solution to this. I'm not even sure, that there are any nice, clean solutions, but it turns out there's some approximations. And how does that approximation work? In this example, there's only one optimal transport, right? If theta is here, you have to move theta. If theta is here, you have to move only this much. Right, so in this case, if I had the optimal transport, the loss is going to look like this. That make sense? Right. And so clearly the optimal transport loss is more useful than your KL loss or the Jensen-Shannon divergence loss, because it's actually sensitive to the distance that you have to move the masses to make the two distributions look like one another. Unfortunately, we don't really know how to compute the optimal transport, because as I said, it's an NP-hard problem. That makes sense to all of you guys? Right. But then it turns out that there's actually some approximation to make. When I'm thinking of moving one distribution to the other, then what you find over here is that this loss, what is the slope of this loss over here? What is the slope here? Come on, guys, don't stare at me, please.
Positive.
It's positive. Is it positive? What is it? It's how much the distance I have to move is this distance, right? The height. So can everybody tell me the slope is 1, 1, 2, 3?
The slope is 1.
All right, okay, you guys there. That lady there, she's sleeping, the slope is 1.
Yeah, the slope is 1.
Right. Can you tell me if the slope is 1? Yes? I'm speaking to. The slope is 1. All right, okay. So this is a clue I'm going to use. I'm going to literally say that this discriminator, I'm going to say the gradient of the discriminator must be 1. I just add this as an extra criterion to my loss. And so here's what I have. The upper one is I'm looking at the expected value of d of x over the training data minus the expected value of d of x over the synthetic data. So that's one component of the loss, which tells me how different the two distributions are. But I'm not stopping at that. I'm adding this extra gradient penalty, which says how much I penalize it if the derivative of the discriminator itself diverges from 1. And that's based on this very simple picture to the left, where you say that in the trivial case, the slope is capped by 1. In fact, in every case, the slope is capped by 1. Is that making sense to everybody? Right? And so this, and then for this to work, you want the weight matrices of your generator and the discriminator to have singular values no greater than 1, so they normalize these things as well. Yeah.
On the left side of the slope would be minus 1.
The magnitude.
At the back.
Okay, you're really looking at magnitude over here, right? So, okay, and so that's about it. And so the Wasserstein-Gann gradient penalty loss is just your standard discriminator, but then you add this extra term which says that the discriminator slope must be as close to 1 as possible. And once you do this, it's not a huge change to your overall objective, except now you're actually computing second double derivatives, because when you minimize the loss, you're minimizing the gradient of the gradient, right? So with that extra term, you actually get some very nice pictures. So here are two examples. One is a Wasserstein-Gann, the other is from a standard Gann. Can anybody guess which is which?
Top one.
Yeah?
The top one is much.
The top one has more variety and just seems cleaner, right? The bottom one seems to be the same picture over and over again. And so you have, the bottom one is showing this instance, it's poorer quality outputs, mode collapse. So in fact, you can generate examples of your kind and you'll see that the WP GAN is generally much nicer. So we learned a bit. We saw a little bit about least squares GAN and Wasserstein-Gans, which addressed some issues with the standard KL divergence. What more can we do? The picture that we just saw, I learned a GAN, it's going to generate outputs. But if I've learned a GAN on lots of images, but I wanted to specifically generate a face, then I want to give it additional input, saying, generate a face. So this is conditioning input. And so this gives us conditional GANs where you actually have an extra conditional variable, typically a one-hot vector, which you can provide to both the generator and the discriminator to determine that it's doing the right thing, generating data of the right class, okay? And you have other things like progressive GANs where you keep increasing the size of the images, style GANs where you change styles. But style GANs are specifically used in image-to-image translation, so let's take a look at an example, right? So let's say I have black and white. This was one of the biggest uses of GANs early in the day. We had lots and lots of black and white movies, black and white pictures, and people to use them to colorize them, and they did a pretty good job. So let's say I want to have this picture to the left of a butterfly, and it's in black and white, and I want to make it colored, right? Or let's say I have this street scene, something, a photograph taken in the night. I want to convert it to something that's been taken in the day. What happened? The style of the picture changed, right? And so here's how they would do it. Typically, if you want to change the style of this picture, what you would do is have examples. I have the same picture in bright sunlight, the same picture in the night. I can have lots and lots of pairs of these. And then I can just train a mapper, right? But in the more generic case, you're not going to get this. If you're going to get data of one kind in one style, data in the other style, you're not going to get, the same picture in two different styles. I mean, Van Gogh didn't draw in both Monet's style and Van Gogh's style, right? It's paint. So how do you perform things of this kind where you change something that's in one style to something of a completely different style where you don't have paired instances? And it turns out you can use GANs for these. So this is what they call the cycle GAN. I can put in my data. I have a model which is going to convert this guy. And so if I'm trying to say convert black and white pictures to color pictures. So the black and white picture would go into the network, out would come a color picture. And then I have a discriminator which just looks at it and says, is this a color picture or not? Color picture or not, right? So, or I could say, I put in a photograph, I want to convert this to Van Gogh style. So I have a network which takes a standard photograph, it generates a Van Gogh style painting. And then I have a discriminator which says, is this Van Gogh style or not? There's a problem with this. The model might just take a standard Starry Night painting and output the same thing every time, right? And so the discriminator is going to be fooled, but you didn't learn anything useful. So to account for this, you go back from the output back to the input and say, okay, now take this Van Gogh style painting and make it back a photograph, right? And then I have a discriminator on the front end saying, is this a photograph or not? And so when you cycle it, you're not allowing this kind of mode collapse. You're not allowing this kind of unnecessary, foolish answer. And so here's the overall training process. You'd have examples of X. Examples of X are going to be converted to Y and back to X. And you'd have a discriminator loss out here and a comparison at the input. After cycling, has it come back as itself? And you do the same thing the other way. You'd have pictures of examples of Y, which you'd convert to X, and then bring it back to Y. You'd have a discriminator at X, saying, is this the right class of output or not? And then when you bring it back, has it changed? And you train the model. And the original paper which did this has had a lot of very nice examples. A painting which has been, a photograph which has been turned to a painting and back. A horse which has been turned to a zebra and back. Things like that. And so now this, of course, is only good for two classes. So what if you had multiple domains? They have something called the star GAN, where you can actually have a conditional generator, which takes conditions, and you can convert things into many different styles. And of course, since we're coming to the end, you can do the same thing to convert text to images. Anyway, in closing, GANs were the first breakthrough in high-quality synthesis and generation. And the key piece over here was that rather than trying to learn the distribution of the output, you learned what is this? Pardon me, okay. That's my mom. Boy. I'm sorry. Okay. The key thing over here was that instead of trying to learn a distribution, you just try to learn a discriminator which said, is the output what you want or not? And so this concept of having a discriminator, turns out, is really very powerful. And it's very powerful even outside this purely generation paradigm. And so it's used in many places. I'll stop right here. Did the class make sense to you guys? Okay. Thank you. We'll see you next time.